Okay. Um, can someone confirm whether I'm audible or not? Okay. Thank you. So yes, once again, welcome to another session for technologies for clean and renewable energy production by Professor Mandal from IIT Roorkee, and I'm Harishankar. I'm a PhD scholar from IIT Madras. So for the last 2 weeks, we were discussing mainly about coal. So we looked at how coal is produced, processed, and used, and we looked at the different properties of coal. Something like moisture, elemental properties, proximate properties, and so on. And we looked at how coal is used to produce energy, mainly in the form of electric power or electricity. So yeah, the major focus for the last two sessions were on coal. So this time we'll look briefly into another source of energy, which is petroleum. And yeah, so this is what we'll be focusing for today. But before we move into this petroleum, so last class, one person had asked me a doubt regarding how this equation was derived. So I just thought I'll give a very quick and brief derivation on how this equation came to be. So yeah, so once that is done, we can move on to the petroleum and solve some assignment questions from previous year questions. Okay, so yeah, let's consider a coal which only has carbon and hydrogen, and the gases that come out of this coal. We were looking at this equation for syngas production and efficiency, and syngas is a gas produced from the gasification of coal. So they have given that the gases mainly contain only carbon dioxide, carbon monoxide, carbon dioxide, hydrogen, methane, and ethane. So we'll also take the same gases. So carbon monoxide, carbon dioxide, hydrogen, and methane and ethane. So how this gasification is performed is by passing air. So air will be passed to the coal at high temperatures, and air will contain mainly nitrogen and oxygen. So using air, we will be gasifying coal to produce these gases: carbon monoxide, carbon dioxide, hydrogen, methane, and ethane. So in effect, if we consider the balance of the whole gases, along with these gases, there will be two more gases: nitrogen and oxygen. Now you must have heard something like theoretical requirement of oxygen and so on. So basically what that means is whatever oxygen that is being passed is used for gasification. Right. So usually what happens in gasification is we don't give the coal the maximum the required amount of oxygen to fully combust. So full combustion you will get carbon dioxide, and partial combustion is where we get products like carbon monoxide, methane, and so on. So since we are since we are supplying only partial amount of oxygen, that means the product will not have oxygen in the case of gasification. But if it was combustion, then you can expect some amount of oxygen also to be present in the product gases. So now our gases at the end are only carbon monoxide, carbon dioxide, hydrogen, methane, ethane, and nitrogen, right? So what we do to get that equation is write the nitrogen balance. So how we can write the nitrogen balance? It's basically, because nitrogen is inert, whatever nitrogen that goes in should come out. So let's say we don't know the amount of nitrogen that goes in, but instead we know the amount of air that we are passing through. So that means how we can find the nitrogen content from air. So we know that 79% of air is basically nitrogen, right? So let us say we know the air flow rate, and let us say the unit they have used for flow rate is nm cube per meter second. So we'll also use the same unit per second. So we know the airflow, and if we just multiply this by 0.79, that will be the nitrogen that goes into the gasifier. Now, what about the nitrogen that comes out? So the nitrogen that comes out, let's say we know the amount of these gases: carbon monoxide, carbon dioxide, hydrogen, methane, and ethane. We know the amount of gases that comes out of the gasifier except for nitrogen. So how can we find the amount of nitrogen that comes out? Basically, like the difference basically. So let us say there is 1 mole of gas that is coming out. So 1 minus the sum of CO plus CO2 plus H2 plus methane plus ethane. So this will be what? Nitrogen that comes out, or the fraction of nitrogen that comes out, right? So all these are actually I am expressing this CO, CO2, all these are I am expressing in terms of fraction. Okay. So now we have the fraction of the gas. Now what we have to do is we just need to find out how much amount of gas that is coming out of the gasifier. So the amount of nitrogen that is coming out will be this fraction, which is 1 minus CO plus CO2 plus H2 plus methane plus ethane, the whole into gas flow rate at the exit. And this unit can also be represented as nm cube per second. So by our balance, whatever nitrogen that is going in is the nitrogen that is coming out. So if we equate this, so this air flow rate into 0.79. So air flow, which is in nm cube per second, into 0.79 will be equal to 1 minus this whole gases expression into flow rate at exit. So I'll just write it as exit flow rate, which is nm cube per second. So basically this is one form of the equation that is given here, this equation. So it's a different form, but we are expressing, instead of here they are using nm cube per second, I mean nm cube per kilogram. we are trying to express it in terms of nm cube per second. If you want to express it in nm cube per kilogram, we can also do that. So we have our unit nm cube per second, and let's say if you want nm cube per kg, then that means, to get nm cube per kg, all we have to do is nm cube per second divided by kg per second, right? Or in other words, if we divide this exit flow this air flow that is going in by mass flow rate. So let us go back here. Yeah, I think there's a small mistake here. Where's the eraser? Yeah. So if we divide this exit flow by mass flow rate, we'll get it in nm cube per second. So if we rewrite this airflow into 0.79 will be equal to 1 minus this sum of mass fraction of these gases into the exit flow, which is basically the amount of syngas that is flowing out divided by mass flow rate. And if we rearrange this equation, okay, need one more slide, I guess. Yeah. So if we rearrange that equation, we can say syngas that is going out or syngas being produced in nm cube per kg will be equal to air flow rate, which is in nm cube per second, into 0.79 divided by this 1 minus the sum of all the gases fraction into mass flow rate, which will be kilogram per second. So this is the equation. This is how this equation for say fuel gas production or syngas production is derived just by doing the nitrogen balance. Because one reason why we are using nitrogen balance is that nitrogen is inert. So nitrogen usually doesn't react with any of these gases at the gasification condition, or it is relatively inert, I would say, compared to carbon, hydrogen, and so on. So that is why we usually use for almost all the combustion and gasification process, we try to use nitrogen balance, to find out our let's say production rate or feeding rate and so on. So yeah, so I hope this derivation is clear, and I mean, I don't think the derivation will be asked in the exam, but yeah, just it's good to know how this equation is derived. Okay, yeah, I hope this derivation was clear. I forgot the name of the person who asked this doubt, but I hope he's also able to understand how the equation is derived. Anyways, let's move on to today's topic. So today's topic, as I said, will be focusing on petroleum. So Professor Mandal's lectures have been covering a variety of topics on petroleum, from the origin of petroleum to how we can use this petroleum and how the distillation process is done, and how some middle products are also processed and so on. So I hope you guys have gone through those lectures. And just to reiterate something that I have always mentioned in all the classes, this session is supposed to act as a supplement to what Professor Mandal is teaching. This is not. This should not be regarded as a replacement or a shortcut or something for those lectures. So as usual, I won't be like going into detail of what Professor Mandal has been teaching in the videos. I'll just go through the contents using the slides that he have been using, and I'll go through some of the old assignment questions, not the current ones that's been used in previous years, based on the topics that has been covered in this class. Right. So we all know what petroleum is. So the word petroleum origins from two words. Petra basically means rock, and oleum, which means oil. Or so, in other words, petroleum basically means rock oil, and it is a mixture of naturally occurring organic compounds from within the earth that primarily contains carbon, hydrogen, and oxygen. So these three are the major organic compounds that is present in this petroleum. And of course, there will be some small amount of nitrogen, sulfur, and metals. So crude oil is what we get from by drilling the earth and trying to mine the petroleum. So crude oil is a complex mixture of hydrocarbons, basically paraffins, which are single bonded compounds, or straight chain or cyclic aliphatic compounds. These are single bonded straight chain aliphatic compounds. Naphthalene are usually cyclic compounds, and aromatics. You must have heard something like benzene from your chemistry classes. So those kinds of aromatic compounds. So crude oil is a mixture of all these three compounds, and it is usually brownish black in color and is colloidal in nature. And petroleum is a broad category that includes both crude oil as well as other petroleum products. So this table, it is giving a brief, elemental composition of the crude oil that that is usually obtained from petroleum. So you can see the carbon is pretty high, above 80% in all the types of crude oil that we get, and hydrogen also above 10% by weight. And of course, you can see some amount of nitrogen, oxygen, sulfur, and metals. Very trace amount of metals can also be there in petroleum. So, if you look at the availability of petroleum around the world, the total world oil reserves, so 15% are found as heavy oil, or the fractions that are present in this crude oil are very having a long carbon chain. So something like let's say greater than C25. So these kinds of oil are usually heavier in nature, and that is termed as heavy oil. So 15% of this world oil reserves are in heavy oil. Then the conventional oil 30%, oil sands and bitumen. So bitumen is something that we use for road tarring, and it is one of the highest or purest form of coal. And yeah, and the world reserves by region, if we take more than or at least approximately half of this petroleum reserve is found in the Middle East or the Persian Gulf countries like Saudi Arabia, Iran, Kuwait, and so on. And in Asia, which includes India as well, barely 3% is found in India. So as you can guess, most of our petroleum requirements are met by importing petroleum from these countries that have high amount of petroleum reserves, mainly from the Middle East countries. So of course there are a variety of types of petroleum that is found around the world. So light crude oil. So the different types are mainly light crude, medium, and heavy oil. So how are these classified? They are classified based on their API gravity. So what is this API gravity? We'll look into it. But basically, API gravity is kind of a measurement that is commonly used for crude oils. So for our other liquids, for example, like water and our solutions and so on, we usually use something like a density, kilogram per meter cube, and so on. So just like that, for petroleum and petroleum fuels, we use API gravity. So API stands for American Petroleum Institute. So we use API gravity for that. And in terms of the classification, you have something like a West Texas Intermediate, which is an extremely high quality of crude oil with an API gravity of 39.6 and a very less sulfur content of 0.24. So crude oils that have a very less sulfur content are called as sweet crude oil, and if sulfur content is high, then it is usually termed as sour, crude oil. So, for example, something like a crude oil like OPEC reference basket A, which is the crude oil from the collection of Middle East countries and other countries like Indonesia, Nigeria, African countries, basically. So you can see that sulfur content is very high, approximately 1.8%. So, yeah. So these are just some of the classification of petroleum that has been talked about. And usually we use these West Texas Intermediate and Brent and this OPEC reference basket. These are usually used as reference crude oils. And these reference crude oils play have a huge impact on how the price of crude oil will be for that day. So usually these three are used as the reference for pricing of crude oil. And yes, the petroleum products, basically the crude oil, we process the crude oil by a process called distillation. So distillation basically means you put crude oil through flow the crude oil into the distillation column. So this column is a distillation column, and you can see there is a temperature gradient across this distillation column. So what happens is basically your lighter compounds which boil very easily. So something like gases. So these gases could be like LPG. Okay. Yeah. So these gases could be something like LPG and so on. So these gases escape first because their volatility is very high, or their boiling point is 20-degree on average, and then comes naphtha, which are so this LPG will be somewhere from C1 to C4, or carbon chain 1 to carbon chain 4, and then C5 to C9 will be naphtha. Then comes your petrol or gasoline that we use for our bikes and cars, and then comes kerosene and aviation fuel. You can even say jet fuel after petroleum. Then after this jet fuel comes the diesel. So diesel is usually used for trucks and trains and so on. And then after diesel, the other fractions are basically the heavier fractions. So mainly they'll be used as lubricating oil or fuel oils in ships and furnaces. And then the final residue is the tar or bitumen, and that will be used for road applications. So the crude oil composition, yeah. So if you look at the crude oil composition, there are mainly two types of compounds that are present in crude oil. One is hydrocarbon, which basically means hydrogen, carbon, and oxygen, and then non-hydrocarbons, which also can contain something like nitrogen, sulfur, and metals. And in hydrocarbons, as I previously mentioned, aliphatics or paraffins. So they usually will be somewhere around C1 to C60 carbon chain length, and they will be usually straight chain or branched chain aliphatic hydrocarbons. And then you have aromatic hydrocarbons, as I mentioned, something like benzenes or naphthalene and so on. And then naphtenes, which basically means cyclic alkanes or cycloalkanes, something like a cyclopentanone or cyclohexenone, hexenes, cyclopentenes, and cyclopentanes and cyclohexanes and so on. And then non-hydrocarbons basically will be the same hydrocarbons, but they'll have either sulfur, nitrogen, or oxygen that are attached to their bonds. And in some cases, metals are also present. So these are non-hydrocarbons. So basically, these compounds together form the crude oil. And this is just a table giving the boiling ranges of all these different kinds of hydrocarbons. So you can see as the carbon number increases, the boiling point also increases. So higher the carbon number, higher their boiling point. And crude oil pricing. So as I said, usually these prices are done based on these reference crude, such as this West Texas blend and Brent crude blend and so on. So usually high sulfur and heavy crude will have a very low cost due to the fact that this high sulfur heavy crude requires a lot of extreme complex processing to convert it into petroleum, diesel, and so on. So that is why usually these will be the cheapest, but then low sulfur and light crude are of the highest quality, and they'll also cost you the highest amount. And this doesn't require such complex extreme processing. Also, crude pricing is a function of the location. So as I said, Middle East countries produce like nearly half of the world's crude oil. So that means if you are someone from the Middle East countries, the cost of buying petrol or diesel will be comparatively less compared to someone from, let's say, India, who have to import these fuels from foreign countries. So location plays a major part in deciding the value of this crude oil. Then you also need to consider the supply versus refining, centers of crude oil in that place. So refiners close to crude production enjoy advantage over refineries that are distant from supply. So as I said, a refinery in in a Middle East country will usually be able to procure crude oil at a much cheaper cost compared to someone from, let's say, India. So So yeah, as I said, this West Texas Intermediate, also known as Texas Light Sweet, is one of the reference crude oils that are used for pricing the crude oil around the world. And on top of that, other influencing factors for crude oil pricing would be supply and demand fundamentals, OPEC policies. OPEC basically means Organization of Petroleum Exporting Countries. So these countries could include some most like many Middle East countries, for example, Iran, Iraq, Kuwait, Saudi Arabia, and so on. Then political or economic developments in the exporting or consuming countries also plays a factor, and weather conditions. So let's say the weather conditions are harsh and shipment takes a longer time or more expense is incurred for shipment, that can influence the pricing of the crude oil. So all these four factors play a very important role in pricing the crude oil around the world. So these are some of the properties of crude oil. So it could be something like density, as I said, from API gravity, and the list goes on all the way up to heating values or HHV and flash point. And to find the amount of or the find the impurities that is present in crude oil, we also measure something like water content, salt content, sulfur content, nitrogen content, basic sediment and water, inorganic and total acid content, and trace metal content. So these are some of the measurements that we use to measure the impurities present in the crude oil. So density and API. So as I said, we use density for our normal, water and other day-to-day solutions. But for petroleum industry, they usually use API, which, as I said, is the short form of American Petroleum Institute. So API, the formula for API will be 141.5 by specific gravity minus 131.5. So this will be the formula of API, and the specific gravity. Just a second. Okay. Yeah. So the specific gravity will be density of the crude oil by density of water. So that is how crude oil or the API gravity of crude oil is measured. And then you have aniline point. So aniline point basically measures how much amount of aromatics are present in the crude oil. So how they usually measure it is by mixing equal volumes of aniline with the crude oil or the oil that is in consideration, and the temperature at which this two mix of aniline and the oil, the temperature at which this forms a single phase upon mixing, that temperature is known as the aniline point. And by using aniline point, we can also measure something called as a diesel index. And the formula for diesel index will be aniline point in degree Fahrenheit into API by 100, where API is the API gravity. And yeah, apart from this aniline point and diesel point, we can also measure total acid number, which the formula will be the milligrams of potassium hydroxide used to neutralize all the acids by gram of crude oil that we have used for this titration. So that will give us the total acid number. Okay. I think okay, fine. Fine. So as I said, the crude oil might have some amount of impurities, mainly metals like metals in the form of salts. So in any refining process, desalting will be the first step in refining the crude oil. So basically in desalting, what we do is we mix water and this crude oil and let the water we let the salts that is present in the crude oil dissolve in the water, and we can separate it by a different separating process. So that is what desalting process basically means. So desalting, you can have two types of desalting process. One is gravitational desalting process, and the other is electrostatic desalting process. So in, okay, I think yeah, the names I mismatched, I think. Yeah. So where is it? Yeah. So this is electrostatic, and this is gravitational. So basically the concept is same. As I said, we'll have crude oil, and this will be mixed with fresh water, and sometimes demulsifier agents or flocculant agents are also being used. And once these are mixed, they'll be sent. They'll be the salts will be allowed to dissolve in this fresh water, and then this will be separated either by using an electrostatic separator within the electrostatic desalting process, or by gravity settling method, because water is heavier than what crude oil. So water along with the salts will settle at the bottom, and desalted crude will come out at top, and this effluent water will be rich in salts. So these are the two different types of desalting method that are usually used in the refineries. Some of the important variables that affect the desalting performances are settling time, or the amount of time that is required for the metals or impurities to settle down in the water phase. Then the type of demulsifier that is used, temperature of the desalting process. So temperature definitely has an effect on the viscosity and density of the crude oil as well as water. So temperature also plays a decent part in desalting process, and the amount of fresh water that is added. So if we don't add enough amount of water for the salts to dissolve and precipitate, then the desalting process may not be effective. And also we need to ensure effective mixing of oil and water, as well as the demulsifier chemicals um, in the process. And in the case of electrostatic precipitator, electricity is also an important factor. So the first case in gravitational desalting, this is a main formula that is used to find the velocity, the settling velocity. The downward velocity or settling velocity of the water droplets in the desalting process, in the term in case of gravitational desalting process. And in the case of electrostatic desalting process, we use the formula F is equal to K E square D raised to 6 by S raised to 4, where F is the electrostatic force, E is the voltage gradient, K is the dielectric constant for crude oil and water system, D is the diameter of the water droplets, and S is the center to center distance between the adjacent droplets. So just running through these formulas. So in the case of gravity settling, V is the settling velocity, R is the radius of water droplet. Delta rho is the difference in density between the oil and water. G is the gravity, and eta is the viscosity. So just make use of this formula. So if we want to find how much time or what is the velocity of this settling of water droplet in the desalting process, we can use this equation in the terms of in case of gravitational desalting process. So yeah, these were some of the major topics that was you know taught by Professor Mandal for week 3. And apart from this, I think he goes into detail about the distillation process as well as other processes such as whisk breaking, coking, and so on, cracking, and so on. So I hope you will go through his lectures as well to get a detailed idea regarding all these processes. But for the time being, we'll move on to some previous year assignment questions. Okay. What is the typical carbon percentage in crude oil? Um, yeah, we just learned about it today. The percentage of carbon is very high in crude oil, and the right answer here is between 83 to 87%. What is the API gravity of medium oil? So we learned there are three types of oil: light, medium, and heavy, all classified based on their API gravity. And for medium oil, the answer is between 22.3 and 31 API gravity. What are the influencing factors for crude oil pricing? So for crude oil pricing, supply and demand is one thing. Um, 1 second. I'm having some issues with my Bluetooth. So let me just reconnect my headphones. Okay, I'm having some issue with the Bluetooth headphones actually. So just give me a couple of minutes. I'll try to rectify it, and we'll resume this class. Yeah, I think I'm having some issues with the um, Bluetooth. Actually, I'm not able to connect it for some reason. Um, can you confirm whether I'm audible just like this without the Bluetooth headphones? Okay. Um, I guess we'll just continue like this. I hope it's audible. I hope it's audible, I guess, for you guys. But anyways, yeah. So what are the factors that influence the crude oil pricing? So supply and demand are one of the important factors. Also, the political and economic developments in the exporting or consuming countries, as well as weather conditions. So all these factors play an important part in crude oil pricing. So all of these is the right answer. In which techniques the crude oil is separated? So we saw the technique that is used, which is fractional distillation. Okay. The next question, the table shows the octane numbers of some hydrocarbons. Hexane has the lowest octane number of the four compounds listed. What structural feature of hexane contributes to this? So hexane is C6H14. Basically, 1, 2, 3, 4, 5, 6. So hexane is a straight chain compound with 6 carbon in it. So out of these 4 options, hexane has a straight chain is the right answer. The next question, the API gravity of natural gasoline and kerosene are 85 and 55 respectively. Determine the difference in their specific gravity. So earlier we noticed that the formula for API gravity will be API gravity equal to 141.5 divided by specific gravity minus 131.5. So if we rearrange this, we can write specific gravity will be equal to API plus 131.5. Sorry, there is a small mistake here. Yeah. Okay. So specific gravity will be equal to 141.5 by API plus 131.5. So by using this formula, we can find the specific gravity of gasoline as 141.5 by API of gasoline is 85. So 85 plus 131.5, and that would be just use a calculator. So 141.5 divided by 85 plus 131.5, and that would be 0.6536. And in the case of specific gravity of kerosene, it would be 141.5 divided by 55 plus 131.5, and that would be 186. So that would be 0.7587. So the difference in their specific gravity would be 0.7587 0.87 minus 0.6536. So if we do that, 0.6536. So that would be somewhere around 0.1051. So out of these three answers, 0.105 is the right answer. In the next question, we have same amount of aniline and a loop sample is heated under specific conditions, and these are mixed at 80 degrees Celsius. If the specific gravity of the lube oil is 0.90, determine the diesel index. Okay. So for diesel index, we have this formula. Diesel index is equal to aniline point at degree Fahrenheit into API by 100. So what we have to first do, so they have given that the aniline point is 80 degrees Celsius. So we need to first convert this 80 degrees Celsius to Fahrenheit. So 80 degrees Celsius will be 176 degree Fahrenheit. Also, they have given the specific gravity of the loop sample. So from specific gravity, we need to find the API gravity. So API will be equal to 141.5 divided by specific gravity, which they have given us 0.9 minus 131.5. So if we do this calculation, 141.5 divided by 0.9 minus 131.5. So that would be 25.72. So now you just substitute all this in the equation. Diesel index will be equal to 176 into 25.72 divided by 100. So if you do this, 176 divided by 100, and that would come somewhere around 45.27. So out of these four options, the right answer here is 45.27. Okay. Fine. The next question. During desalting process, after coalescence, the water droplets containing this salt settle down in a desalter. How would the settling rate of these droplets change if the viscosity is reduced to 1/3 of the original viscosity by increasing the temperature? So this is a gravitational desalting process, and they are asking us, if we increase the temperature and decrease the viscosity to 1/3 of its original value, what would be the velocity in this new case? So for gravitational desalting, according to Stokes' law, we have this formula, which is the settling velocity V is equal to 2r square delta rho into g by 9 eta, where V is the velocity and eta is the viscosity. Now let's say this is case 1. So we use V1 and eta 1. Now we are increasing the temperature, and they have said that the viscosity at the second case eta 2 will be eta 1 by 3. So let us try to find the new velocity here. So this V2 will be 2r square delta rho g by 9 eta 2, and because eta 2 is n1 by 3, it will be 2r square delta rho g by 9 eta 1 by 3, or this will be 2r square delta rho g by 3 eta 1. So this is V2. Or if we equate this V1, equation 1 and equation 2, so let's say we are equating 1 and 2 by doing equation 1 divided by equation 2, or V1 divided by V2 will be 2r square delta rho g by 9 eta 1 divided by 2r square delta rho g by 3 eta 1. So all these terms will get cancelled, and V1 by V2 will be 9 by 3. Or in other words, V1 will be 3V2. Or the new velocity is 3 times the old velocity. Hence, the right answer here is that the velocity will triple. Okay. So one more question. The API gravity of West Texas Intermediate crude oil is 41.6. What will be the volume of 1 metric ton of this crude oil in a barrel unit? So we have the form. So what they are asking us to find here is that they have given the API weight or API gravity of a crude oil, which is the West Texas crude oil, WTI crude oil. And they want to find what will be the volume of this crude oil if we take 1 metric ton or 1 ton of this crude oil. What will be the volume of that crude oil in barrel units, not in liters or anything or meter cube, in barrel units. So first we'll be using the formula for API gravity. We have that formula. API gravity will be 141.5 by specific gravity minus 131.5. So from this, let us first try to find the specific gravity of this WTI crude oil, and that will be equal to 141.5 divided by API plus 131.5. So if we substitute the values here, let us do the calculation. I'm using a calculator here. So 141.5 divided by API, which is 41.6 plus 131.5, and that will be 0.817. So that will be the specific gravity of the WTI crude or West Texas Intermediate crude. Now we have this specific gravity here. So in 1 kg, how much liters of crude oil can be there? And that will be 1 divided by 0.817. Right? And this will be 1 divided by 0.817, that is 1 divided by 0.817 will be 1.224. So in 1 kg, you have 1.224 liters. And 1 ton will be 1000 kgs. So that will have 1224 liters. But they don't want us to find it in liters. They want us to find it in barrel units. Okay. So we have in 1 ton 1224 liters. So 1 barrel unit is 159 liters. So in 1 ton, how much barrel unit will be there? That will be 1224 divided by 159. And that will be somewhere around 7.7 barrel units. So the right answer here is 7.70 barrel units. Right? Okay. So we'll stop here at this point. I do apologize for the inconvenience for the final few minutes. I'm not sure why, but my Bluetooth, I'm still unable to connect my Bluetooth to my laptop. So hopefully I'll be able to rectify this soon. But anyways, we'll stop at this point. And yeah, I hope the session was useful to you. And yeah, I hope you will be able to solve the current assignment problems as well based on the concepts and the example questions that we solved during this class. And yeah, fine. We'll stop here for now. We'll meet next Sunday, same time at 3 o'clock.